Hello again. Hope you're enjoying so far. Our next speaker is Kevin O'Brien. Kevin is a data scientist based in the west of Ireland.
Hi there.
Uh, Hi. Kevin has been very active in the data science community over the past decade and is now a director of Python Ireland, the YR Foundation, and R Forwards Task Force, and social media chair of Julia Khan. He was formerly a mathematics and statistics lecturer at the University of Limerick. He will talk about a new approach for the method comparison problem. So just a kind reminder, you can ask him questions, and after his talk, he will
Yep.
answer them. So yeah, I mean,
That's great. Thanks very much. So I'm just going to switch over to my slides, and I'm just going to put that into read mode or full screen mode, and I'll just go through them there. So my name is Kevin O'Brien, and while it says I am a director of Python Ireland, really this is not really connected with Python. This is more connected with my regular day job as a forestry data scientist, where I would actually use R a lot. Also, actually, as said, I actually was a former university teacher, and that's sort of why I'm using Beamer, because I still use it for statistics and computing presentations. So a little bit of background to this, actually. So this is the method comparison problem. So I'll set up a little bit of the background to it. This is in the context of medical statistics, also clinical statistics, pharmacy statistics, and actually all sorts of natural science statistics. This is, again, actually very current because of the year that we are in, that a lot of medical statistics are now being discussed in the news media quite a lot. So it's sort of interesting to sort of revert to that. We're all data scientists. We all are familiar with the likes of confusion matrices and ROC curves and stuff like that. But it is interesting to sort of see the parallels, what's going on in the in the medical statistics world and the clinical statistics world. So this topic is used quite a lot in clinical research. This is called method comparison studies. Now, in one way, it's a very simple topic, but in other ways, it's still quite open. It's still quite interesting about a lot of the characteristics related to it. So again, so just actually sort of highlight the point, I just have some screenshots here. I'll go through them very quickly. But essentially, the medical statistics are very important in clinical research, and even very much so the idea of method procedure comparison. It is a vitally important topic. So that's just a sort of quick reminder. Now, I realize that some of these are out of date, but just to sort of emphasize that point, that this is quite an important topic in clinical research. So let's just start with some fundamentals. So we're looking at some medical devices here. We have methods for measuring blood pressure, and also we have a method there for measuring blood sugar level, a glucometer. Now, just in the bottom corner there is a blood pressure cuff, which is also known as sphygmomanometer. Sphygmomanometer. I messed that up. I'll keep going anyway. That's probably a very useful example, because that's a lot of things that people will be familiar with. They've all had their blood pressure taken. They're all familiar with the cuff going around their shoulder and being pumped up, and two measurements are taken. So this is a sort of the type of measure that medical statistics would be interested in, internal measurements. Height, weight, so on, those are sort of simple measurements, but the likes of the blood pressure measurements, they're a bit more difficult to take. So measurement is always looked at in the from the context of two components, accuracy and precision. So this is a well-known thing. Now, we are going to look, accuracy is straightforward enough, really, and so we won't look at it that much, but precision is quite an important matter. And considering the type of data we're going to be dealing with, we actually would sort of consider ourselves having two types of precision. One we're going to call precision, the other we're going to call repeatability. And I'll come to that shortly, but this is the sort of the fundamentals of it. Now, just actually as a quick remark, I sort of touched on this point earlier, is that the idea of a medical measurement, sometimes there is quite a lot of cost or overhead associated with getting that measurement. So it's important to be accurate, but it's important important that it's feasible to make the measurement. Now, this is a sort of an extreme example, but if you consider that other types of medical measurement might, for example, like the coronavirus things, they put a swab in your nose. That's essentially a medical measurement. So there is sort of, a cost or lack of comfort involved with them. So that's a sort of important consideration. So the method comparison study sets up two common scenarios, and one is a very common scenario. So often we have a reference method, a very accurate, or at least most accurate method, but there's some overhead or cost involved in getting it. Sometimes it may take a lot of time to get the measurement, or it might cost a lot, or it might be invasive. Another what we might compare it against is a test method, which is probably not as accurate, but it's more has less cost involved, so it's more usable in the real world or for wide scale use. So we might be interested in using the test method, but we want to know how good it compares against the reference method. And that's the basis of what a method comparison study is. So just here's a sort of quick example of what I mean there. This is actually how we might sort of measure body mass index. Now, comparing against the gold standard is the most accurate way, or the most accurate possible way of getting a measurement. But so here for body mass index, the most accurate way of getting a measurement might be actually to submerge you in water and look at the displacement. But as you can imagine, that's actually quite tricky to do. That's quite a tough thing to do for a lot of people. So other methods were devised that would be quicker. So using calipers there just to measure body fat folds on the skin. It's much quicker to do, and no one gets wet, and you don't need a lot of equipment either. So you can sort of see that as preferable, but also you want to it's good to know that you have a proper method to compare against, a benchmark, so to speak. That's a bit of an extreme example, I grant you, but I think it's the type of thing that most people would be familiar with. So I'm just going to move on from this. This is sort of some other examples here. This is a sort of where it pops up in the real world. This is a sort of old example. This is air pollution example from using sensors to measure air pollution on a bicycle. This is just a newspaper article from a few years ago. So now I'm going to get into more detailed the terminology. So I just touched upon the gold standard there. Gold standard method of measurement is the most accurate possible way of getting a measurement. And so there's this is a definition. There's a lot of definitions around this. So it's the most accurate test possible without restrictions, okay? And it may yield a value close to the true value, and then again it might not. So this touches back to the idea of accuracy and precision, that how close we are to the true value, which is the real value, not the measurement. There's always some sort of error, and how often we can repeat that measurement. So this is the idea of a gold standard measurement. So it's sort of important in the context of this. Now, the idea of gold standard measurements is actually quite tough. Actually, I sort of should show you here now, just a sort of little bit of a read through of this, but it just to sort of say that even a gold standard measurement could actually be not that accurate, particularly when we're dealing with internal body measurements. Not that it's not accurate, but we know that there's even a gold standard measurement would have an associated error, and sometimes in some topics or some disciplines, it could be quite substantial. But it's the best you got, so it's what you have to work with. So the point really is that sometimes a gold standard is still not considered a perfect measurement. Okay. So that's just a sort of just a quick remark about gold standards. Now, I realize there's got quite a lot of material here, so I'm going to have to go through it quite quickly. So I won't dwell on it too much. Now, so I'm going to sort of break this down a little bit more. So what we're asking is two particular questions. So the two questions really are, do two methods of measurement agree statistically? And can the two methods be used interchangeably? Okay. Now, the second question there, can the two methods be used interchangeably? That's a sort of very straightforward definition. Does one method give you the same results as the other method? So it's quite a strict definition. They actually are very close in measurement to one another. The first question there is a bit more practical. Do they agree with each other statistically? And that sort of raises the question, how much tolerance do you have for lack of agreement? How close do they have to be in terms of agreement? So if so that's really it. The sources of disagreement are the key thing here. So one could be differing population means. That means an intermethod bias. Okay, an intermethod bias could mean that one measurement consistently gives you a higher value or a lower value compared to the other measurement. Okay, so what it could be on average +2 units more. Okay, now this is actually quite easy to fix. This is the type of thing that the t-test, which we might have learned in undergraduate statistics, would test for. So it's actually straightforward enough to detect. It's straightforward enough to verify using statistical procedures, and it's straightforward enough to correct using calibration of machinery or making a correction factor. So it's straightforward enough. The other two types of the sources of disagreement are the between subject variances, do they differ, and the within subject variances. Now, those are very important technical terms. So essentially what I'm going to call them is precision and repeatability. And I'm going to come back to those two. But those are the terms that we would sort of be looking at in terms of statistical terminology. Okay, so that's the framework there. Now, there's quite a lot of material in and packages set up for this in R. Okay, so the R programming language has a dozen packages set up for clinical research and also specifically method comparison studies. So for what I'm going to describe is mostly based in R, in the R packages. Okay, so CRAN is a comprehensive R archive network, and the clinical task views is essentially a compilation of a lot of R packages related to clinical trials. And so that's just a sort of screenshot of that page. Okay, so this is one in particular I'm very interested in. So method comparison studies. So functions for analysis of agreement in method comparison studies. Actually, the real reason I sort of mentioned this is one of the author, the main author there is Bendix Carstensen. So he was one of the pioneers of using linear mixed effects models for method comparison studies. And this is the first package that really implements it. Also, there are some of his colleagues there who also contribute to the package. So some of the data sets I would use would actually come from this package. There's one I'll introduce very shortly. So moving on. Okay. Now, this is a very important distinction. Okay. So there's two types of method comparison studies. There's one where we have a single measurement per person, per item. A subject is a person or something you're testing or measuring. And you have a single measurement per person or per subject per each method. And each method would be taking a simultaneous measurement. Okay. So in that case, there's one measurement by each method, by each person, by each method on each item. Okay. Now, the subject of this talk actually looks at more at the point of view of the second case, where there is multiple measurements per subject per each method, by each method. And that's the basis of the approaches discussed here. In the first instance, the established approaches are sufficient. I won't go through them all. I'll go through the main one, but for the second one, there's still a lot of, lot still to be determined for the second case, multiple measurements. And that's why linear mixed effects models, which I'll discuss shortly, would fit in there, because I think they're perfect for it. So that's just to sort of clarify that in this talk, we're really working at the second case, which is replicate measurements, multiple measurements. Okay, so that means that there might be 2 or 3 measurements for each person by each method. So they could have 6 measurements per item altogether. Okay. Just a sort of quick remark, the blood data is a data set used, and it's available on the MEthComp package. And this is the sort of the main data set that people would sort of use to compare their methods. It's a sort of like the iris of method comparison studies, if you pardon the uh, comparison. So it's about measuring systolic blood pressure. There are 2 experienced observers, J and R, and also a blood pressure cuff. I'm not going to pronounce it again, denoted S. Oh, sorry. There is a semi-automatic blood pressure monitor denoted S. Okay. So in this context, in this setup, we have 3 devices, 3 measurement methods, J, R, and S. And on 85 patients, 3 measurements were made in quick succession. So this is the sort of typical data set that people would use when they're talking about method comparison study, or they want to test how their procedure would work. This is a very commonly used data set. So the systolic blood pressure data. So I'm just going to use that shortly. Just a sort of quick remark, that's just a quick screenshot of it in R. So just give you a sort of quick sense of how it's structured. This is actually a very important matter in this subject, is sort of setting up the data properly. And this is just a quick look at the systolic blood pressure data set. Method J for the first 3. The item 111, 3 replicate measurements. So the measurements are 100, 106, and 107. So they are all 3 replicate measurements made by method J on item 1, all at the same time. So they are supposed to be close to each other. So yeah, likewise, there's R and S. So they are 98, 98, and 111. Those measurements are supposed to be very similar to the methods, the measurements made by J. So that's the point of that. And likewise, S. Now you can sort of see that S is much higher, and that's obviously a problem. So S is 122, 128, and 124. Okay. So there's 3 conditions of agreement, and I'm going to talk about these shortly. So I just touched upon them there: accuracy, precision, and repeatability. Now, precision and repeatability are the 2 key ones there. Okay. So essentially, repeatability is, does the method agree with itself? And precision is, on average, do the methods agree with each other? Okay. So repeatability is the key one. Precision and repeatability are the key ones. Accuracy is not so important. It's easy to test for. So I'm just going to sort of skip through this here. Something I'd like to sort of point out is the main procedure here is called the Bland-Altman plot. And I'm just going to sort of just show some slides here, because there's a lot of detail here, but you can sort of read up about it. So essentially, it is a very simple plot, okay? And it consists of, I'll actually just show the code here. I'll just show you what. This is a Bland-Altman plot, okay? So it's a sort of a depiction of the case-wise averages for a pair of measurements compared to the case-wise differences. So the average of 2 paired measurements versus the difference, okay? And it's a very simple to construct plot. And actually, this is all the R code that was needed to construct that. Now, I'll just sort of let you have a quick look at that there. But really, the point of that is, if you're having a quick read of that, you realize that that is actually not very hard at all. Okay, that's the type of thing an undergraduate would learn in their first R programming course. Okay, with some simple, just some quick, simple data or classes. Okay, so very simple construction to that. That's actually quite important. Now, it's very simple to interpret. Essentially, it works the same way as a residual plot. Okay, so you just, for example, I just talk through a couple of examples here. In this instance, you might be looking at the distance from the top to the bottom. This is what they call the limits of agreement. It's a sort of an expression of the range of the differences. And here it's measured as mean plus or minus 2 times the standard deviation of the differences. So it's essentially the width there is the sort of key thing there. Okay. You might be also looking for outliers. Sorry, that's a little bit hard to tell there, but you might be looking for outliers in your plot. Okay. Or trends or variances or lack of variance. Okay. So it sort of would work the very same way as a residual plot that you would probably have learned about in undergraduate statistics. Okay. Now, this is the interesting thing about it. And this is what I find so interesting about it is how prevalent it is. Okay. Building blocks just actually, I believe it comes to the fact that it's just so easy to construct. But I'll just actually quickly show you this is actually, sorry, 2020. This is actually very recent. It was actually not May 2015. This is actually November 2020. This has in excess of 45,000 citations, the paper that proposed this. Okay, and this is actually, I believe, a very interesting point. That's a lot of citations and it's one of the most cited papers of all time, actually. 47,000 actually just updated that since. That's a lot. That's one of the most cited papers of all time. In fact, it's actually got recognized as such in Nature. Now, this is an article from a few years ago. The 100 most cited papers of all time. They actually had a quick review of them. Okay, and they found that this Bland-Altman plot, which is the test that the paper that proposed this procedure, was 29th. Now, this is a little bit out of date. It actually has doubled since. At the time of writing here, it was 23,000. It's now 47,000. Okay, so it's been a huge success. Now, just as a quick remark, in case you're wondering, a lot of the other top 100 papers are to do with laboratory sciences. So they are very popular in terms of research. Okay. So I don't want to spend too much time in that, but just actually as a sort of quick remark, there was one of the other ones, the popular ones there was the Kaplan-Meier curve. But this is just a sort of a quick remark that the Nature made about it. Okay. Now, essentially what actually the sort of comment here just down at the bottom is that the same idea was introduced by another statistician 14 years earlier. That's just sort of making the point that it's a actually simple idea. Now, credit to Bland and Altman for correctly sort of proposing it and promoting it very well. That's just a sort of quick remark there, just something I'm going to sort of pass on up for another time. But actually, I noticed that somebody is cross-validated actually was talking about residual plots as if they were modified Bland-Altman plots, which is sort of a telling in a way that they actually sort of did not know the name of a residual plot, but they actually did know of a Bland-Altman plot, and they just called a residual plot the modified Bland-Altman plot. Now, I don't want to sort of I don't want to criticize them. They actually obviously have quite a good statistical intuition, but it just sort of tells a lot about the relative prevalence of the two. So that's just a sort of little bit about the Bland-Altman plot. I'm going to sort of skip on to the next bit because just a sort of a quick remark there is that there are actually other procedures. I'm going to just skip past a bit. This is what they call a folded ECDF plot, also known as a mountain plot. And here, what I have here is created here is a mountain plot for comparing the three measurements, systolic blood pressure measurement methods, J, S, and R. I find this very simple to use. Essentially, J, which is in blue, and R, which is in pink. You can sort of see that they overlap quite a lot. And we would sort of surmise, we would suppose that they are actually in quite a lot of agreement. They do agree with each other. So this is actually a very useful approach for assessing the agreement between the two. We also have S there, the semi-automatic measurement device. And obviously you can sort of see that is obviously quite distinct from the other two. So we would sort of suppose here that J and R actually have quite a lot of agreement, whereas S is obviously not agreeing with the other two. Its measurements are completely different from the other two on the same patients. I actually like this approach, and what I'm interested about it is that I think it's very easy to use, very easy to explain, but nobody uses it. Okay. Now there is a couple of factors. It does require a certain sample size. In this example, just a sort of I'm going to sort of remark upon here. This is sort of second example for a different data set. I won't go into it so much, but here you can actually sort of tell the slight differences between the two. So we have a pink trend line here and a blue trend line. And the idea is that they overlap. If they overlap with each other, they are in agreement. Now, this is sort of where the gray area sets in, where we have to be subjective in our decisions. And this is why this blood pressure, or sorry, this mountain plot would help us, because we can sort of see that the pink line, trend line, is sort of outside. It almost covers the blue trend line, but they are still quite close. So they're not in perfect agreement, but we know that they're close. Okay. Now, I sort of say it's mean-centered here because they're actually, I've taken out there was inter-method bias in this example as well. So I just mean-centered it to take that out, just to make that point, that this is actually quite a good approach. Now, I'm going to sort of skip past this, actually. I'm just sort of realizing I'm sort of have to keep up for time. But actually, just a sort of something to note and make a note about, or sort of further reading is the idea of a technology acceptance model. Very interesting topic. And it's sort of a great way of like sort of considering how a lot of decisions were made, or how we have come to use certain methods or certain approaches, but not others. So anyway, I'm just going to sort of remark upon that the Bland-Altman method, which is the main plot, provides important insights, but is insufficient on its own. And it does not properly account for replicate measurements. Essentially, what you have to do is actually treat replicate measurements as if they were single measurements. Okay, so the idea is actually to develop a proper methodology for method comparison studies, MCS, and get people to use it. Okay, so that's just a sort of quick recap of the three conditions, but I'm going to sort of skip past this to linear mixed effects models. Now, this is the main sort of part of the topic here. This is the real heavy duty science. This is where we fit models. So there's a lot of detail in this, and I won't go into so much detail. I'll sort of stick to some headline topics. So just to start us off, we would look at consider linear models. Okay, and this is the type of thing that people would sort of learn about in statistics courses. Okay, linear models, simple linear regression, multiple linear regression, and so on. Okay, so that is our starting point there. But essentially what we can do here is actually generalize this to linear mixed effects models. Now, linear mixed effects models are essentially, we can consider linear models as a subset of linear mixed effects models. So in linear mixed effects models, there is fixed effects and random effects. Now, there's quite a lot to explain in that. So I'll just sort of say that essentially random effects allow us to use grouping, okay, or incorporate grouping in our modeling. Okay, now that is a very for the purpose of method comparison studies, that's a sufficient simplification. That's all we really need. Okay, so linear mixed effects models allow us to sort of capture the grouping behavior, sort of replicate measurements for each person, and sort of contain them together, or sort of model them simultaneously. Okay. Now, there's quite a few R packages for this, and again, R really is the main sort of approach for using mixed effects models. There are two main packages: the NLME package, which has been around quite a while. That's a book there, mixed effects models in S and S plus. Apologies for not that coming out. Now, this is actually this package is very detailed, and it provides a lot of functionality for creating very complicated models, linear mixed effects models. And one approach actually uses these these functionalities. I'll just come to it shortly. There's another approach here that I'm going to favor later on. It's called LME4. Now, this provides a similar, a simplified approach from my point of view. The syntax is much easier, and it actually provides a way that is more accessible to the general public. Now, this is an important topic. Just to sort of remember one thing about the Bland-Altman plot. People found it to be very accessible, very easy to use, and you know, that's why it was so prevalent. Okay, that's a sort of important consideration for what I'm about to discuss now, because it's great having a very thorough method, but if nobody uses it, then what's the point? So the point really is getting a very proper, useful method, but also making sure that people can use it. You don't need a PhD in statistics. In fact, just an undergraduate statistics course should give you proper grounding for making this sort of analysis. Okay, so this is more viable using the LME4 package, and it's based on the syntax. Now I'm going to go through the next sort of stuff quickly because I realize I'm stuck for time. I'm going to skip over a few things there just to sort of remark that there are other ways of looking at this called R and Julia. Now, so there's an approach here called Roy's approach. And I'm going to sort of remark that they set up a very detailed linear mixed effects model. Okay. This is just sort of going back to the model I discussed previously. And so what they want to do here is, this is the key one here. So precision and repeatability are the two key topics here. So based on the model I've just shown you, it sort of sets up an overall covariance matrix for the response factor, which is the set of responses, the set of measurements. Now, this set framework sets up and it allows the decomposition of the variance into two components. One component there is D, which is the between subject variances, the precision, and the second component there is sigma, and that's the within subject variances. Okay, so this allows us to sort of separate the two out and look at them individually. Okay, now this is the key thing about the criteria. Do they have the same level of variance, both methods? So what we would do is we would look at the diagonals of the two matrices in the middle there, D1 squared and D2 squared, sigma 1 squared and sigma 2 squared. And essentially the question asks to be asked, are they equal to each other? Now, the thing about the LME frame and LME R package is it allows us to create two models, one where they have to be equal to each other, and another where they are allowed to be different from each other. So that is the sort of the key part of this methodology, really. That's it in a nutshell. Okay. Now, there's a lot of very strenuous looking R about to come up here. I'll just sort of move on from that very quickly. So essentially what we're going to do is set up two models. Well, actually, we're going to create three tests, and in each test, there will be two models. And one test, or for each of the tests, there'll be one model used consistently for each of the three tests. That's our reference model. And in the other three tests, there are the nested models. Okay. Now, the idea is the nested model in the nested models, we impose the constraint that the two variances have to equal each other. In the reference model, we allow them to be different from each other. Okay. And so that is it. So I'm going to sort of skip past it, that and just actually talk about the R code. This is the reference model here. Now, so I'm not going to go into too much detail here because this is the type of thing that I probably read about after the fact. So these are some OR models that we would set up an NLME for. So I'm just going to go through them very quickly. So that's the first one there, second one, this is the third one, and the fourth one. Now, they are actually all very similar to each other. Okay, just to sort of remark that the code does look very intense looking, but ultimately it is actually very consistent between the four models. There's just slight variations. So it's sort of difficult in one way, but also easy in another way. The second thing is actually that we are the way we would sort of impose our equality constraints is how when we use these components here. These are the matrix constructions, symmetric and compound symmetric, and that's the code for them there. So that's how we would sort of implement those equality constraints. Now, how do we test them? So I'm just going to sort of move on to the next part here. Just quickly go down to the next part. Sorry, I went past it a bit. Where is it? Sorry. Yeah, there we go. How do we test them? So essentially, when we have created our four models, it's actually very straightforward to actually test one against the other. Okay, so the model construction is quite difficult, but sort of comparing the three models is not so difficult. So that is where we would use the ANOVA procedure, and we would just actually the ANOVA test procedure, which is where we would use to sort of determine which of the procedures is the best procedure. Okay, or sorry, which model is the best fitting model. Now, constructively, that's telling us, do they agree or do they disagree in terms of between subject variance or within subject variance or overall. Okay, so so those are the three types of tests, and just to sort of overall, we would find that they would have no significant difference between subject variances. No significant difference in between subject variances between the two models, but there is a significant difference detected in terms of the within subject variance. Now, this is what the outcome of the procedure would recommend. It is there cannot recommend switching between the two models. Okay. Now, this approach is complicated and intensive, and it does not incorporate clinical knowledge about the data. But also it raises the question, what would it take to fail the criterion of equal between item variances? That's a sort of important question, and it's an important question to ask about this procedure. How do you sort of fail this criterion? And the reason, essentially what that would require is a complete failure of the one or both methods to take proper measurements. Okay, so essentially, this is a very complicated framework, and I think it's actually could do with some reduction, because if there is a failure to take consistent measurements, that means that you should have discerned that from exploratory data analysis. I just realized I'm coming out of time there, so I'm just going to go back to my host.
Hi. Yeah, we're running out of time, and we're like online, so we need to be like really precise about time. Yeah.
Sorry,
So,
sorry. I just sort of realized I was
right.
coming up with
So
time.
if you could like just like try to like, I don't know, summarize or like have a point in like, I don't know,
Okay, so
15, 20
the
seconds.
key thing is that first off, there's two key points: that the very straightforward graphical procedures are very useful. Okay, so it's the time to start exploring at them again. And the second one is that there is a lot of very good approaches there for linear mixed effects models, but the thing is actually to sort of don't reduce it down in terms of complexity, because what I just showed you at the end, I realized it was just very, very complex. That there was going to be no sort of getting around that. It was just a very complex problem. The linear mixed effects models are very difficult. So
Thank you very, yeah.
okay,
Thank
so
you
I
very
have to go
much,
now. Yeah.
Karen.
Thanks very much.
Yeah, unfortunately, we need to move on. Thank you very much once again.